going to look at stationary waves, our last topic in waves. You know them?
Yes.
Mm-hmm. Anything go down?
Yes.
Yeah. Okay. Okay, so what is a stationary wave? It's also called a standing wave. Go for it, KJ.
Wave that is stationary.
Wow. And a standing wave is a wave that's standing, is it? It's a wave that moves in one position. So I think the easiest way to see this is with a picture. So let me try and draw this as well. So what you might have there could be a wall here, and then there's a little machine here with a wheel on it, and then you tie a rope here, a wheel or whatever, and this is moving up and down, and it makes a wave in the rope. But the way the wave moves, it makes it look like this shape, because the wave is going up and then it goes down, and then this one goes down and then this one goes up. So it almost looks like just this. Like a fish, yes. And you can kind of see that in the picture I have here with the rope. So the idea here is that the wave is not moving anywhere like a sound wave. It's just staying in one spot but moving up and down. This is a stationary wave. Do you understand from my picture? Yeah?
It's for music or something.
Yeah, like pulling a string on a guitar, something like this, yeah. Got it? Yeah? No? Yes? Yes or no? Yes? Okay. So how do these waves happen? Well, to go back to the example with the wall and your rope, the wave is like this, for example, and it starts to move towards the wall. And then what happens, I draw it here. Then it reaches the wall, and then when it hits the wall, it bounces back. So if you look at this, down, up, what's next then is down.
Yeah.
So when it hits the wall and travels backwards, well, what the wave wants to do is it wants to go like this, but it can't because the wall is here. So instead, this part gets flipped around and it will travel backwards like this. And then it will hit the wall here and it wants to continue going down, and then it'll flip around and go back like this. So that's why it keeps switching between the two. So this is how you can make a standing wave. So you can see that it's very important that you have the length of the string correct and the length of the wave correct. So in this example here, this, well, there's not in this example. In this example, the string is equal to the wavelength in this example. Okay. Right, let's go on. So when you have standing waves, you have two parts of a standing wave called a node and an antinode. And basically, the antinodes are the parts that move the most, whereas the nodes are the parts that look like they're not moving. So if I go back to my picture here a moment ago, you see this point here and this point here. These are called the nodes. These, this point and this point, this one and this one, this one and this one, these are called the antinodes. So the node is the place where it is minimum, and then the antinode is the place where it is maximum. Come on, you can do it. There we go. So these are the antinodes, and then here at the minimum places are the nodes. Please make note of this vocabulary, nodes and antinodes.
Which way like hit the wall and continue the voice wave and
No, they usually, like in my picture, you have to tie a rope against the wall and shake the rope.
yeah, anything there's some. I mean, which wave can like hit the wall and continue?
Continue?
Yeah.
Not continue, it can hit the wall and reflect.
I know for this one it reflects, but is there another wave like to continue?
Invisible wave.
Well, a radio wave would go through the wall.
Probably.
You know, the waves coming from your mobile phone, you can still use your mobile phone in a room that has no windows. So the wave from your phone will go through the wall. Yeah? Not sound waves though. Well, not really sound. If the wall is thin enough, the sound waves can go through. If it's thin enough. Okay. Can I go on? No? Did you write all of this down?
Yes, when I was sitting outside, I was wondering, like, I can like listen to your voice.
Mm-hmm.
So the
In this case, I guess the wall's not so thick. Yes? Continue? No? Continue?
Yep.
Are you sure? Grace?
Yes.
Great. Now, in fact, if you know the distance between the nodes and the antinodes, you can actually work out the wavelength. It's very easy. So let's imagine I have a standing wave. Here it is in red and blue. So it's like this. And also it's like this. As it's vibrating up and down. Now, for example, what is this called? Node or antinode? And here? Antinode. So let's call this distance here, for example, x. If you look here, oops, in black. If I draw a little box here, this is one wavelength from here to here. So this distance here to here is actually half a wavelength. I didn't draw it so well, but you get the idea. From node to node or antinode from antinode. So in other words, the distance from node to node or antinode to antinode, that's equal to half the wavelength. Okay. There's a lot here, but I think a picture might be best. So in the example with the rope against the wall, here's the wall, and here's the boy or whatever turning the rope. That's one wavelength. But you could have done it like this. In other words, you could have fit in two waves, for example. So there's more than one way to do this. So I suppose if we think about a musical instrument, so you know, like a guitar. Do you know a guitar? Do you know guitar, Grace? Yeah, you do? Show me. Show me. Yeah, guitar. So if we have a guitar, we have one string. Like this. So for example, one possibility is if we pull the string up and make a wave like this, which is only half a wavelength, isn't it? Because there should be a piece that goes down as well. Yeah? This is called the first harmonic. And look, here's a picture of all the different types. So if you pull your string like this is called the first harmonic. If you manage to get the string like this with one full wavelength here, then this is called the second harmonic. And this one here, you can see, will be the third harmonic. Whoops. And the fourth harmonic, and so on. So, it's just a little bit of vocabulary. Also, the first harmonic is also called the fundamental. So this is the fundamental harmonic, second harmonic, third harmonic, fourth harmonic. So you need this to happen if you want to hear a note, a musical note. So we have first, second, third, fourth, and so on.
With one wave, that's first harmonic. One harmonic, right?
The first harmonic is half a wavelength on the string.
And the second too, right?
No, the second is one full wavelength, and then the third one is 1.5 wavelengths. Then the fourth one is 2 wavelengths. Yeah. Yeah. Okay. So, the situation is a little bit different for musical instruments that use wind or air. So, it's a tiny bit different in these situations. Let me try and draw them. So, you have two possibilities. This is an open pipe where the air can go in and out at the back. Okay. And what I was trying to say here, is when a sound wave is formed in a pipe, there'll always be a node at the closed end and an anti-node at the open end. So here this is open and this is open, which means there must be an anti-node here and there must be an anti-node here. So it means I'd have to draw my wave like this. So, yes. And then one upside down as well. So this is the smallest wave I could draw because I must have an anti-node here. Anti. Can you see that? Anti. How many nodes do I have? How many nodes? Two. Here and here are my nodes. So in this picture, this is called the first. Now, how much of a wavelength is it? Is it one wavelength? No, I think it is one. Yeah, it's one. It goes from max to min to max. So, can you see the difference in my original one here? Oops. The first harmonic was half a wavelength. Whereas for our instruments that have air going through two open ends, the first is actually one whole wavelength. Now, let me try my very best to draw the second. So remember, I still need to have an anti at this side and an anti at this side. Don't confuse me. There we go. So this is the second one. So you can see here there are how many wavelengths?
Looks like 3.
It's 2 actually. No, is it not 2? Hang on, let me count. Hang on, I'll count. 2. Yeah, it's 2. Node, 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 and node. 4 nodes now. Yeah. Can I draw the next one? Well, there's only one more. So the second air pipe is closed at one end. So that's when you have a pipe and this side is closed and this side is open. And in these situations, there is a node at the closed end. So here there is always a node. And at the open end, it's the same. What must I have at the open end? I must have a antinode. Yes? Just like in the last one. So if I draw my wave, this is what the first wave looks like. Whoops. How much is this? How much of a wavelength is this? No. It's less. No. It's only a quarter because it still has to, if I zoom out a bit, the wave would still have to go down and then down again and back up to here. So in fact, it's only a quarter. And this is called the first again. Okay. And let's draw the second as an example. So again, I need a node. And here I must have an antinode. So I think I'll go like this. Yeah. I think. No. I don't think so. Node. Yeah, no, maybe I was right. Sorry. It's hard. Hang on, let me just draw a little wave here. Okay, I want to start here. Yeah, I want to finish on this one. There we go. That's what I want. And here is a node. So this one here is the second harmonic. How much of a wave do I have here? Very good, KJ. It's 3/4 of a wave here. Huh? Say again? Between these two? Well, in this one here, it goes from node to antinode. But this one here goes from node to antinode to node back to antinode. So there is more here. Like this first one only goes to here.
You say it's the third part. On the left is closed, on the right is open. But why have two different pictures?
Oh, it's the same picture. This is open here. This is an arrow. Never mind. This is open here. Why two different pictures?
Yeah, why are the different ones?
Oh, these are the different possibilities. So, like with my example with the boy against the wall, he could make this wave, or if he wanted to, he could make this wave. You could have two of them. But he couldn't really make this wave where he has, I don't know, one and a little bit. There's only certain possibilities you can have. In fact, sorry, I don't think we call this one the second. I think we call this one the third. And the second is not possible because the second would be to here. But we can't finish on a node. We have to finish on a antinode. So we only have the first and the third and the fifth and the seventh. No second or fourth. Because we must finish on an antinode.
So this is a...
Yeah. So this would be a pipe. And the back of the pipe is closed and the top is open. And
you said third.
Yeah. The second is not possible. In this situation, KJ, we're going up in quarter wavelengths. So we can have a quarter, we can't have a half, but we can have 3/4.
So that's going to be the fourth.
Huh?
This one will be the fourth.
No, this one is the third.
The one on top is the first.
Yes. Yes. I know, it's a little bit confusing. We'll do some examples now. Can I do a question? I think I have a question coming up. Okay, so the first one is the boy against the wall and he vibrates the other end, so the first harmonic stationary wave is formed. What is the wavelength of the wave formed? Okay. So here's the boy. And he's 2 meters from the wall. And he forms the first harmonic. The first harmonic means the first wave he can make.
It's halfway.
In this case here, oh sorry, yeah, I drew it wrong. In this case here, yes, it's like this one. So what is the wavelength?
1/2.
No. No, you need to look at the picture.
Under what you,
So the wave is like this, look. Up, down, like this. So the wavelength is actually from here to here. So how big is that? 4 meters. His wave actually goes down. So it's going up and down like this.
So whole one way is 4 meter.
Yeah.
And halfway is 2 meter.
Yeah. Mm-hmm. So the answer is 4 meters. Yeah. Let's have a look at the next one. Another one. So, okay, so what you have here, in this question, I tell you there is a pipe, and the pipe is, I think I said, 17 centimeters, and then you make a sound wave using it. You could use a tuning fork. Have you seen these before? You hit them on the table and it makes a note. Yep. Have you seen these? Tuning forks? Huh? I don't know about hospital. You know the ones I'm talking about? Yeah, it's a fork shape and you hit it on the table and then it shakes and makes a note. Yeah. So you know that this one here is frequency is 500 hertz. And what you do is you make a wave here and you make the first harmonic. Okay. So here, do I want node or anti-node at the bottom? No, node. It's closed. And up the top here? Anti-node. So the first harmonic is this wave. So how much of a wave is that? How much? A quarter of a wavelength. So you have a quarter of a wavelength equals 17 centimeters. Yeah, so first we'll find the wavelength. So what's that? Let me see, 50, 68? 0.68, is it? The question is asking me for the speed of the sound wave. So, we know this and we know this. So can anybody remember a formula to get the V? Anybody? The speed of sound. I forgot. Lambda F. Remember this formula? So that will equal 0.68 times 500, which will equal what? Is that about 340, is it? So that's how fast sound moves. That's the speed of sound. Or sound wave, if you want. Now, you know, so like if I take this, so what you do here is you have your fork and you hit the fork on the table and it makes the note at 500 hertz, and then you put it over the pipe, and if there's a standing wave, then the pipe will start to vibrate a little bit. So in this experiment here, if you use 500 and if you use 17 centimeters and you strike it, then it'll shake. Now, what you do in the experiment is, let's imagine this is 20 centimeters, and I strike it. Will it vibrate? No. 20 centimeters is too long. You wanted 17 centimeters. So what you do in the experiment, you take some water, so you hit this, you put this here, and then you start pouring water in, and it'll make it, the pipe smaller. And then you keep pouring the water until it starts to shake. So now you've made a standing wave. So this is a simple experiment, and it'll let you easily calculate the speed of the sound wave. Okay? So it's not so difficult. And in fact, this question, I don't know why, this question is very common in the exam. A bit like in the last lesson, there's not too many different types of questions. This one is a popular one, but it's only 2 marks. Well, because it's so short. Okay, did you write it down?
Yes.
Yeah. How are we doing for time? Loads of time. Loads.
10 minutes.
Yeah. So the answer is 340.
Exercise.
Okay. Exercise. Dang.
I said 2 marks.
2 marks.
I said the example I did is 2 marks. They're not that long because, like, for example, question 1, 2, and 3 are basically the example I did. 1, 2, 3, the example I did. No, 1, 2, 3, 4 are like the example I just did. Only 5 is difficult. So look, 1 minute, 1 minute, 1 minute, 1 minute, 10 minutes maybe. Huh?
Absolutely no.
Absolutely
Just
yes.
The tennis will do 1 minute.
Huh?
Tennis will do.
No. No, even KJ could do it in 1 minute.
1 hour. 1 hour.
Yes. This is usually my opinion.
Is it really?
Yes.
We'll do it later today together. No, don't pack up. You have a few minutes left, so you can start them now, so we can do the answers later today. Okay, so you can take a picture on your phone if you want, and you can start them now. Now. And later, we will do it together after you have tried them first.